Hi, here is another video from SolverScape. We provide scheduling solutions for problems arising in logistics and supply chain management. So today we are going to talk about the weekly planner. Let's say you are a service provider who manages a set of facilities. Each facility is open 7 days a week from 6 a.m. to 8 p.m. Customer demand at the facilities varies at an hourly level. You need a weekly plan for your staff working at these facilities. A worker works for 5 consecutive days. A worker shift is 8 hours long with a 1 hour break during that 8 hour shift. The number of workers required in each hour at each facility is known. The weekly planner finds the minimum number of workers and their weekly shifts so that each facility has the required number of workers in each hour. So, how do we call or access this model? We do that via this application called the Solver platform. It acts as an interface between a user and the mathematical model. Data interchange between the user and the model occurs via Excel. A user fills a specific Excel template and passes the file to the Solver platform for processing. The Solver platform calls a specific model, gets the model solution, and passes it back to the user in Excel format. Let's look at a demo now. So here is the application, Solver platform. We have 3 tabs here: models, jobs, and queue. Let's look at the jobs tab, which gives the list of historical jobs. So let's look at a job for the weekly planner. So we have a lot of information here. Let's get this job in Excel format by clicking on this link. So now we have this job in Excel format. Let's open the file. So we see there are different tabs here. Let's go through them one by one. So the first is the parameters tab. This is where we set the boundaries for this particular problem. So here we have a working planning horizon of 7 days. Each day has 24 hours. Each shift has 8 hours. We need 5 shifts in the planning horizon. Each facility opens at 6 a.m. Facility closes at 6 p.m. There are at least you need to have at least 14 hours between the end time of one shift and the start time of a subsequent shift. Then a user can say, oh, I want to have the break that is at least 3 hours after a worker's arrival and is at most 5 hours after a worker's arrival. We can also have a constraint for the maximum number of workers. So then we have the solver settings, which we can skip for now. We have the facilities. We give 5 facilities here and their latitudes and longitudes. Then we have a set of workers, 100 workers in this particular problem. Then we have the worker requirements at each facility on each day in each hour. So then these numbers are just varying randomly between 3 and 7. So this is just synthetic data. So what's the solution that the model gave? Here is the solution summary. The model said that you need at least 99 people to meet the requirements at all the facilities. So how does the work plans look like? So let's go to these plots. So here is the plot for the work plans. So the model came up with, let's see how many. It came up with 83 work plans. So each of these colors indicate different facilities, and then the gray here indicates when a person gets a break. So then we also have the plot for which worker was assigned to which work plan and so on. So then we have a plot for how well we met the requirements at each location. So as you can see, for example, at Handsome in time period 6 on day 0, we needed 4, we gave 4. So there is no access here. So there are a few places here where you do see the access, and that is inevitable because the demand is varying. But what the model is doing is it is telling you how to have the minimum access here. So you are using the fewest number of workers. So how do we know the quality of this solution? So for that, we need to talk about a concept called the optimality gap. It is the difference between the cost of a given solution and the cost of the best solution. If the best solution has a cost of say 10 million, then moving from a solution with a gap of 11% to a solution with a gap of 1% will result in a saving of 10%. which is equal to 1 million. So what was the optimality gap for this particular model? So for that, we go to the solver statistics tab, and we see here the model was actually solved in 4 different stages. And we have a gap value for all the 4 stages, and we see that the gap value is less than 1% in all the stages. It's actually 0% in 3 stages. So we can be sure that we are within 1% of the optimal solution. So conclusions, the model can be enhanced to include complex business rules. We can also provide an API endpoint for this model. The model is based on a technique called mixed integer programming, and it can be applied to large size problems with hundreds of workers and facilities. The information on optimality gap can lead to significant savings. ML AI based models provide quick solutions but without any information on the optimality gap. MIP models are best suited for planning problems that do not need to be solved in real time but involve upfront capital allocation. To know more about where we have applied our models, visit us at solverscape.com/case studies. For potential collaboration, write to us at contact@solverscape.com. Thank you.